For question 5.55, we need to draw the shear and bending moment diagram for the beam and loading zone. And we also need to determine the maximum normal stress due to the bending. So this is the figure that show the value of force, and also there is a distributed loading here. The first step that we should do is we need to find the free body diagram by using this figure. So we can get the force of RC, RB, and FC. These force have given in the equation, which is 2 kN. To get the force FCB, which is the force of the distribution loading, we need to times it 3 kN per meter times distance 4 meter, and then we can get the value of FCB is equal to 12 kN. So we can get the value of RC and RV by using the submission of F equal to 0. Then we just equate it into the equation negative 2 kN plus RC plus RB minus 12 kN equal to 0. Then we can get the first equation of RC plus RV equal to 14 kN. And then to find these two value, we can take the moment at B. So we use the submission MB equal to 0. Then we times 12 times 2. 12 we get from the FCB times 2 is the distance between the C and B, and then minus RC times 4 meter. RC is 4 meter from the RB plus 2 times 5. 5 is distance between A and B equal to 0. So we can get RC times 4 equal to 34. Then we can get the value of RC is 8.5 kN. After we get this value, we substitute it again in the first question that we have, which is RC plus RV equal to 14, and then we can get the value of RV is 5.5 kN. And then for the second step, we take the first section, which is we take 2 kN and V equal to downward, and there is a moment here. So this figure is shown the free body diagram for the first section, and then we use the submission of Fy equal to 0. So there is only 2 of y here, force that move downward, which is negative 2 kN minus V equal to 0. Then we can get the V equal to negative 2 kN. So the V is negative 2 kN is from here. And then we go through for the third step by using the same method. So we use the submission Fy equal to 0. Then we just substitute the value of 2 kN, negative 2 kN plus 8.5 kN, which is the value of RC here equal to V equal minus V equal to 0. Then we can get the value of V for the second figure is 6.5 kN. And the fourth step is we take the third section here, and we can get the force 2 kN, RC force, FCV force, and there is value of V here. So we use the submission of Fy equal to 0. We assume the submission Fy is in positive way. So the value of 2 kN must be negative because it's going to downward, plus 8.5 kN and minus negative 12 kN from SCV, and minus V equal to 0. So we can get the value of V here is negative 5.5 kN. So now we can plot the value of V that we get earlier, which is we get the value of V is negative 2 kN, second is V equal to 6.5 kN, and third is V is negative 5.5 kN into this graph. So we can plot it, negative 2 here, and then we just plot 6.5 here, and then negative 5.5 kN here. This show is happen because there is a distribution loading happen here. So to plot the bending moments graph, we need to find the moment at A, C, T, and B. And then we assume that moment at A is equal to 0. And then moment at C, we can get it when 0 minus 2 kilonewton, which is negative 2 kilonewton. This value of negative 2 kilonewton, we can get it when the moment at C minus moment at A, and then we can get value of negative 2 kilonewton. Moment at D, we can get it when negative 2 plus 7.0418, and then we can get the value of 5.04183 kilonewton for the moment MD. The value of 7.04183, we can get it when MD is minus MC is half times 6.5 times 2.1667. The value of 2.1687 is the ratio between these two figures. Then we can get as 2.1667. And then for the moment at B here, we can get it when negative 5.0416 plus 5.0418 is equal to 0.0002, which is equivalent to 0 kilonewton. And then this value, negative 5.0416, we can get it when the moment at B minus moment at D by using the formula of half times negative 5.55 times 4 minus 2.1667, and then we can get the value of negative 5.0413 kilonewton. So for the second questions, we need to find the maximum normal stress. So we need to find the maximum normal stress for the pipe. So the formula is S equal to I over C naught. And then the formula of I, we can get it by using the equation of pi over 4 times C naught to the power of 4 minus C1 to the power of 4. And then we can get the value of 1.3312 times 10 to the power of 95. To find the C naught, we need to divide it into 2, which is 160 times 10 to the power of 93 over 2. We get the C naught is 0.08 meter. And then C inner is 140 times 10 to the power of 93 over 2. We can get the value of Ci is 0.07 meter. And then we substitute it into the equation of I. Then we can get the value of 1.3312 times 10 to the power of 95. So we just put this value into the formula of I over C naught. C naught we have got it is 0.08. So we divide it I 1.3312 times 10 to the power of 95 over 0.08, and then we can get the value of S is 1.6641 times 10 to the power of 94 meter per square. And then for the formula of maximum normal stress is the moment at D, because the moment at D is the maximum point. So 5.0418 times 10 to the power of 3 over S, which is 1.6641 times 10 to the power of 94, and then the value of maximum normal stress is 30.2975 in megapascal. So for the second question, which is the question of 5.83, we need to assume that upper reaction of the ground to be uniformly distributed, and knowing that the allowable normal stress for the steel used is 165 MPa. Select the most economical wide flange beam to support the loading shown. The figure for us to solve this question. So the first step that we need to do is we need to find the free body diagram, which is that the question stated the upper reactions of the ground is uniformly distributed, which is in here there is the distributed loading force, which is it moves upward. So the step is also same with the earlier questions. So we just use the summation of Fy equal to 0. So 0 is from A here. There is no force acted on it. Plus 444.44 times 1.2 minus Vb negative is equal to 0. Vb negative we can get the value is 533.328 kilonewton. This value of 444.44 kilonewton per meter, we can get it by divided 800 kilonewton times 2 over 1.2 times 3, which is we can get the we can know that the distance from A and D is 3.6. So we can get the value. So the third step is also same as the second step, which is we use the submission of Fy is equal to 0. Then we substitute 533.328 is from here, minus 800 kilonewton minus Vp plus is equal to 0. So the value of Vv plus is negative 263.672 kilonewton. And the next is also same. The step is also same. We use the submission of Fy is equal to 0. So 533.328 is minus 800 kilonewton here, and we plus 444.44 times 1.2 minus Vc minus equal to 0. So we can get the value of Vc minus here is 266.656 kilonewton. So we noted it as FCB. And then next is also same. We use the submission of Fy is equal to 0. So 533.328 minus 800 plus 444.44 times 1.2, it is from here, minus 800 kilonewton is here, minus Vc plus is equal to 0. So the value of Vc plus is negative 533.344 kilonewton. So value is Vc plus is here. And the value of Vd, we sum up is negative 533.344 kilonewton plus 444.44 times 1.2, which is here. So we can get the value of Vd is negative 0.016 and it equivalent to 0. So to draw the graph of V and S, M and S, which is for the graph of V and S is we just plot the value that you have given here, which is the value that I have find Vv minus is 533.328 kilonewton, and then V plus is negative 266.672 kilonewton, and then Vc negative is 263.656 kilonewton, and then for the Vc plus is negative 533.344 kilonewton, and then for the Vd is equal to 0. So this value we just plot it in this graph. But for the bending moments, we assume that the value of moment at A is equal to 0, and then MB is 0 plus 320 is equal to 320 kilonewton. The value of 320 kilonewtons, we can get it by using the formula of area, which is area at area A to B is half times 1.2 times 533.328 equal to 320 kilonewton. And for bending moment at ME is 320 minus 80 is equal to 240 kilonewton. So the value of 80 here, we can get the area between B to E, between B to E. So 1 over 2 times 0.6 times negative 266.672. So we can get the value of area B to E is negative 80 kilonewton. And then C is also same. The value of 240 plus 80. So we can get the value of 320 kilonewton. And then also same, the bending moment at MD is 320 minus 320. So the value of moment at D is 0 kilonewton. So we just plot all this value into the graph. And then for the next step, we need to find the most economical void flange by using this formula, which is S min equal to moment maximum over normal stress all. So the question has given the value of normal stress, which is 165 MPa, and then we have got the moment maximum is 320 kilonewton times 3.6 meter, which is the distance between A and D. So we can get the value is 1,152 kilonewton per meter. The value of S min we can get it by by divide it 1152 times 10 to the 93 Nm over 165 times 10 to the 96 Nm negative 2. So we can get the value of S min is 6981.8 times 10 to the 93 millimeter per square. To find the wide flange beam, we can get it from the appendices, which is at page A14 and 815. So we list up all the value that the value of S is larger than S min, which is I have listed about 1, 2, 3, 4, 5 shapes that are suitable because the value of S here is more larger than S min. But in this question, we need to find the lightest shape. So I have choose that W920 times 21201 is the most economical wide flange beam to support the loading. This is because we also noted that the total weight of the loading will be 3.6 meter times 201 kilogram per meter times 9.81 meter per x square is equal to 7,088.516 Newton. This weight is also small compared to 160000 Newton load, and it can be neglected in the analysis.